And so today I'm going to talk about some results that I've obtained in my thesis, which actually got examined last week, so very fresh. And you can find it on my website, a preprint form that contains these words in this title and a few more. So, oh yeah, and I should also mention, maybe I just do that immediately. So I have some slides so that you can follow along on my website, but maybe let me share them here for you. So just very quickly, I'll put them in the chat. So if you want to look ahead or go back, then they're there. All right, so let's get started. So before explaining the results that I'm aiming for, let me sort of try to explain the general context and motivation. So the sort of main motivating question is the following, namely, we start with a family of curves, typically assumed to be smooth, projective, and geometrically integral and defined over the rationals. And we want to study the statistical behavior of arithmetic properties of those curves. So what kind of properties are we after? So, well, the usual suspects. So first of all, the set of rational points. So if you're dealing with an elliptic curve, this would be a finely generated abelian group, but in higher genus, this would be merely a finite set. And so again, in higher genus, it's typically useful to study a closely related group, namely the Mordell-Way group. And that's the rational points of the Jacobian. So here J in this talk will always denote the Jacobian variety of C. And so I briefly mentioned this is always a finely generated abelian group. So it has more structure and tends to be easier to study. And one other reason why it's easy to study is because you can study it using two descent, or in general n descent, but we will focus here on the case 2. And in modern terms, this is interpreted as computing a two-Selmer group. So if you haven't seen the definition of these things, or don't remember, it suffices to know for this talk that this is a finite dimensional F2 vector space. It's defined inside some sort of Galois cohomology of the two torsion of J. And it's defined by local conditions. And it fits in the following short exact sequence, where we start on the left with the mod 2 Mordell-Way group, which injects into the two-Selmer group. And the co-kernel is measured by some failure of the local global principle, which in this case would be the two torsion and Hf group. All right. And so the important thing is that if you can bound a two-Selmer group, then you can bound the mod 2 Mordell-Way group, and this gives you information about the rank of this finely generated abelian group. So the flow of information typically goes this way. So let me give you two examples of sort of theorems that we're aiming to generalize, which I think are both quite spectacular. So the first one is just by looking at the family of all elliptic curves, or Q, up to isomorphism. And every such curve has a unique Weierstrass equation. Well, it always has one, and it's unique up to scaling this coefficient by a 4th power and this one by a 6th power. So if you insist that these coefficients are integers, and no prime P has a property that it's 4th power divide A and it's 6th power divide B, then you can choose this equation in a unique fashion. And all right, so for such an equation, you can define its height. And again, whatever it is, it suffices to know that number of curves up to a bounded height is finite. And using this notation, when you order elliptic curves by this naive height, Bhargava and Shankar proved in this paper is published in 2013 that the average size of the two-Selmer group, where E varies over all elliptic curves, and this should be interpreted as a limit of the average size of the two-Selmer group of elliptic curves of height at most x, and you take the limit as x goes to infinity. this is 3. So the limit exists and it equals 3. And an immediate consequence using this exact sequence that I wrote on the previous slide, bearing in mind that for elliptic curves, their Jacobian are just equal to themselves. The rank of the finally generated abelian group, EQ, is at most 1.5. Okay, and so I just want to mention this because this started off sort of the field in the sense that I'm working on it. And of course, later, Bhargava and Shankar obtained similar results for the 3, 4, and 5 Selmer groups. And consequently, this bound got much better, but I won't mention that further. And since statistics is in the title of my talk, let me show you a graph. So this graph is, I think, the best up-to-date information about ranks of, or the average size of the 2 Selmer group up to a certain bound of naive height. So for example, this point here displays the average size of the 2 Selmer group of curves up to a height at most 10 billion. And it shows that this is around 2.6. And well, they didn't complete the full data on the right, but some large-scale experiments seem to suggest that it does converge to 3, as it should. Okay, I forget to say, but if you have any questions or comments during my talk, please feel free to interrupt. So, all right. And let me move on to the second example, and that's of higher genus curves, namely odd hyperelliptic curves of genus G. So soon afterwards, Bhargava and Gross obtained similar results for the 2 Selmer group of the Jacobians of such curves. And more concretely, a curve in this family, those are just the curves given by the equation y squared equals x to the 2g plus 1 plus lower order terms. So P2, you can omit the first coefficient if you want, P2, etc., and P2g plus 1, where Pi is in Z. And Poonen and Stoll used this result, or rather a more precise distribution result, to show that if you consider the probability that a curve in this family of genus G curves has at most one rational point, in fact, exactly one rational point, namely the marked point at infinity, which is always there if you homogenize this equation, and it's always rational, then the probability that this is the only rational point tends to 100% as G tends to infinity. All right, and so this by now leads to the well-known slogan that most odd hyperelliptic curves have only one rational point. So we're trying to get some generalizations or maybe weaker versions in other situations of these theorems. So to explain how to do that, I must explain a little bit the proof of Bhargava Shankar and Bhargava Gross. So let's do that next. So very roughly speaking, sweeping a lot of details under the carpet, the proof of these counting of the average size of 2 Selmer group, they break up in 2 steps. The first step is an orbit parameterization. So what you do is you need to find a representation V of some reductive group over the rationals, such that, well, certain rational orbits, so GQ orbits of VQ correspond to elements of the 2 Selmer group of the Jacobian of the curves in the family, or the Jacobians of the curves in the family. And then the second step is to forget about 2 Selmer elements and just count integral orbits in this representation. And of course, you need to sieve out the orbits not corresponding to Selmer elements, and you need to worry about the difference between rational integral orbits, but let me not dwell on that further. Let me just give you one example, which actually is very classical and goes back to Birch and Swinnerton and Dyer. And it says that elements of the 2 Selmer group of an elliptic curve correspond to certain orbits of binary quartic forms. And the way that this goes is that an element of a two-Selmer group of an elliptic curve, it gives rise to a 2-to-1 covering of P1, where C has a property that, well, it's a genus 1 curve with Jacobian isomorphic to E, and it's everywhere locally soluble. And in fact, choosing an equation for C, you can describe it as Z squared equals some binary quartic form. And changing coordinates will change the PGL-Q equivalence class of this binary quartic form, or we'll change it by PGL-Q conjugate. So that's sort of a very easy and explicit algebra geometric way. And in general, there are many other orbit parameterizations that have been found using similar but more difficult algebra geometric techniques. And so, in fact, the second step in the Bhargava Shankar case, this is what they used. They used this orbit parameterization and this strategy. But so they already had step 1, so they only needed to do step 2. And in fact, they solved step 2 so well that they solved it for many other types of representations as well. So let me just mention that the second step, and this is a bit of an imprecise statement because they don't write it down that way, but it turns out that the methods to count orbits, they can be applied very generally. So this step has been solved very generally by Bhargava, Shankar, and Gross. And these are typically called geometry of numbers techniques. All right, so really the crux of the matter is in finding the right representation and finding representations of relevance to arithmetic statistics. So that's sort of the cliffhanger question of today is how do we find representations of interest, G, V? And to give a sort of partial answer to this question, let me give you a brief detour in the world of graded Lie algebras. So here's a definition. So suppose I start with a Lie algebra matfrak H over field K. Then such a Lie algebra is called M graded, where M is a positive integer. If there is a decomposition of H in M it's a decomposition in M subspaces with the property that if you bracket the ith part with the jth part, you land in the I plus jth part. All right, so it's a fairly straightforward definition. And why is it useful for us? Well, it's useful because a graded Lie algebra gives rise to a representation. So here I explain it on the Lie algebra level. So how does this work? So the Lie algebra acts on itself via the adjoint representation, just by taking the Lie bracket of 2 elements. So that means that if you call G the 0th part and V the first part, then this relation here implies that if you bracket G and V, you land in V again. So in other words, G acts on V, and G acts on V as a Lie algebra representation. And we can globalize this construction. So if you have an algebraic group, H over K, with Lie algebra H, so you could take, if H is semi-simple, you could take the simply connected form or the adjoint form. And suppose you have a closed subgroup with Lie algebra G, then similarly, the adjoint action of the group on the Lie algebra will restrict to an action of G on V. And the pair G, V is called a Windberg representation in honor of Windberg, who studied the theory of graded Lie algebras. All right. So why do we want to consider those type of representations? Well, from the point of view of invariant theory and classifying orbits, they have very good properties. Properties very similar to just the usual adjoint action of an algebraic group on its Lie algebra. For instance, there is an analog of the Chevalier isomorphism, and well, you also have the notion of a regular element and a semi-simple element, and this makes the classification easier. And so Benedict Gross, when he tried to understand why Bhargava and Shankar could estimate the 2, 3, 4, and 5 Selmer group of elliptic curves, but not the others, and why certain representations appeared and why others didn't, he made an observation, namely that basically all representations arising in the arithmetic statistics literature at that point were Windberg representations. Here, if I'm very precise, I should say that there are a few exceptions. But I can elaborate on that if people want. But basically all of the others, they arise from Windberg theory, so they arise from a graded Lie algebra. And the punchline of this talk, and very, very loosely formulated the main result, is to sort of turn this observation on its head and use it as a starting point. So it says that we can use graded Lie algebras as a starting point to prove, or actually prove and reprove, theorems in arithmetic statistics. Okay, so let me now explain in more detail how that works, unless there are any questions. So, okay, so how does this work? So we're going to use a setup that's due to Jack Thorne's PhD thesis that's been written around 10 years ago under the supervision of Dick Gross. And so what's the setup? So we start with an ADE-Dinkin diagram. And I'm going to sketch to you how you can get from this on the one hand, a Windberg representation, and on the other hand, a family of curves over Q. And the main theorem will relate to 2. So let me explain to you how this works. So if you have such a Dinkin diagram, then from Lie theory, we know that they correspond to simple Lie algebras over C. Not all of them. There are also ones where you have multiple edges between the nodes, but we know that every such diagram corresponds to a simple Lie algebra. And since we work over Q, I'm going to assume that I'm going to take a split Lie algebra H over Q. And in fact, we don't only have a Lie algebra, but we also have we can equip it in a canonical way up to conjugacy with a 2 grading. And its definition, I'm not going to describe in detail because a little bit complicated, but essentially it's uniquely defined by the following 2 properties, namely, first of all, that the associated Windberg representation has stable vectors in the sense of geometric invariant theory. And another way of saying this definition is saying that if you base change to C, it's conjugate to the Cartan evolution from the theory of Shimura varieties. And this pins it down over C, but if you want to pin it down over Q, you have to impose that the first part of the grading, which is a Lie algebra, is going to be a split Lie algebra. So in any case, there is some natural way of considering a 2 grading, which essentially makes no choices. And again, if you choose the adjoint group of this Lie algebra and consider the construction of the 2 slides ago, we get a Windberg representation, G, V. And I'll give you an example in a second. So that's the Windberg representation. How do we get the family of curves? Well, if you've heard about ADE correspondences before, then you might know that these diagrams, they don't only classify Lie algebras, but they classify many other types of objects in mathematics. So for example, they classify the underlying graphs of quivers of finite representation type. And you could fill a whole lecture with what they classify. And the thing that will be relevant for us will be some notions from singularity theory and something that's called a simple singularity. And more precisely, a simple curve singularity. So maybe I move this a little bit down. And if you have a curve singularity, then there exists a process from deformation theory called taking this semi-universal deformation, which in this case is a very explicit thing. And it leads to a whole family of curves whose central fiber is a singularity, but the generic member will be smooth. And if you only take the smooth members, then this process, which is using deformation theory. So this is all a bit of a cartoon. I'm not being very precise here, but just to give you the idea. So using deformation theory, you get a family of smooth curves. Curly F over Q. And so if you've seen a picture like this before, then it might be that you have heard of something called the Briscoe correspondence. And that relates simple surface singularities to Lie algebras in a similar way here. And what it says is that if you take the generic singularity of the nilpotent cone of a Lie algebra, you recover exactly the simple surface singularity of that type. And in fact, something similar is true in this graded situation, namely you can recover this simple curve singularity inside the nilpotent cone of the graded piece. And this you could call the a graded version of the Grothendieck-Briscoe correspondence. Also established by Thorne in his thesis. And so the main theorem relates those two objects, namely it gives an orbit parameterization for the curves in F using the Windberg representation. All right, so I promised you an example. Let's look at the first non-trivial example. It turns out A1 is not interesting, so I'm going to look at A2. The associated Lie algebra is SL3, and we take the adjoint form, so that's PGL3. And giving a 2 grading is the same as giving an involution by considering plus and minus 1 eigenspaces. So I'm going to tell you what the involution is. The involution is given by the inverse transpose, where the transpose here is not considered along the diagonal, but the anti-diagonal. And so you can see that this is very similar to the Cartan involution, except we've modified it such that this fixed point group is split. So if G is this fixed point group and V is this -1 space of the involution, so the first piece of the 2 grading, then G acts on V. And it turns out that using an accidental isomorphism between SO3 and PGL2, that this is isomorphic to the representation of PGL2 on binary quartic forms. Okay. And on the other hand, on the curve side, the A2 singularity is a cusp. So the A1 singularity is a node, and the A2 is a cusp. And taking this process of semi-universal deformation, which is a very explicit process, basically adds some coefficients in a minimal way that deforms a curve. Again, this is very loosely speaking, and it turns out that the family of curves that you get are precisely smooth members of the form like this, where A and B are coefficients in Q. So this is exactly the situation considered by Bhargava and Shankar. And maybe to convince you of what this Grothendieck-Briscoe correspondence, this graded version means in practice, let me show you how you can find the curves inside the representation. So if you consider elements of the representation V of the form of the following form, and this will seem very random, but it's part of the general theory of Slotowee slices, which I won't go into. If you consider elements of this form, where I see this as an element of V, which is embedded inside this SL3, so 3x3 matrix. So we consider elements of the form with a fixed characteristic polynomial, say t cubed plus at plus b. So there is no t squared coefficient because it traces 0. Then this forms a variety if you calculate what the equations mean, which turns out to be isomorphic to the affine curve given by the short Weierstrass equation. All right, so this is already one sign how the curves are related to the representation. So let me now state the main theorem. So suppose you start with a Lincoln diagram, again assumed not to be of type A1. And so as I said, this gives rise to a representation and a family of curves. And the main theorem connects the two. So for every curve in the family, so the first part is that there exists a natural injection from the two-Selmer group of the Jacobian of the curve inside the set of GQ orbits of VQ. And well, natural here means that it has several good properties. It's like compatible with base change if you consider other fields and so on. And in fact, for another good property is that there exist integral representatives away from small primes. And the properties are so good and robust enough so that we can obtain the second part of the theorem. Namely, we can count orbits and get an estimate for the two-Selmer group. So when you order by a suitable height, there exists an explicit integer m, which I'll say something about in a moment, such that the average size of the two-Selmer group of the Jacobian varying over curves in F is bounded above by 3 times 2 to the m minus 1. Okay, so let me maybe pause for 1 second and see if there are any questions about the statements. So, all right, so if not, let me make a few remarks. So first remark is that this upper bound here, this is probably sharp. And the reason I say this is because there is only one part in the argument where the equality breaks down, namely when applying a certain uniformity estimate on values of polynomials which are square free. And that turns out to be a difficult problem in general. And Bhargava and Shankar solved this in the A2 case, so the elliptic curve case, but all the other cases seem to be quite hard. And another remark is that this M has a natural interpretation in terms of the family of curves, namely it's the number of marked elements or marked points rather in F. So in the family of elliptic curves, there's always one marked point, namely the one at infinity, but sometimes there are more. For example, in the A3 case, this is essentially the family of all elliptic curves with another marked point, so then M is 2. And the D4 case would be all elliptic curves with 2 marked points. So, all right, and so using that remark, it's one can see that sort of if this were an equality, this quantity 3 times 2 to the m minus 1 is consistent with like existing heuristics, for example, those of Poonen and Reins, because this would account for the sort of trivial subgroup generated by differences of the mark points in the two Selmer group. Okay. So let me just briefly say a few words about previously known cases of this theorem. So many cases were known already before, namely the A2 case, as I mentioned, is Bhargava Shankar. The A2G case, that's all the hyperelliptic curves. That's Bhargava and Gross. The A2G plus 1 case, that's monic even hyperelliptic curves. That's Shankar and Wang. Jerry Wang. And the D2G plus 1 case, that's hyperelliptic curves with a marked non-wire stress point and a marked wire stress point. And that's done by Anand Shankar, the brother of Arul. And the low cases A3 and D4, which correspond to elliptic curves with some marked points, they were handled by Bhargava and Ho. And so all these theorems, they use the specific structure of the representation and of the curves in an essential way. And I guess the sort of one of the points of my result is that the proofs are uniform. So the proofs of theorem 1 and 2 are uniform. And if I'm completely honest, then there's one step in the part 2 in the orbit counting, which is not uniform. And that's where you need to cut off the cusp, which is some technical part of the counting arguments. But apart from that, for example, the orbit parameterization and the construction of integral representatives, that's all done in a uniform way. All right, and so all these cases that were known before, those were all hyperelliptic curves. Those are all families of hyperelliptic curves. And the missing D even case, so that's the only classical case that's missing, D sub an even integer, that's also hyperelliptic curves. But these exceptional cases, E6, E7, E8, they're interesting because they lead to non-hyperelliptic curves. And let me give you one example of how they look like, namely the E6 case. So the E6 case leads to the following family. Here F is the family of non-hyperelliptic genus tree curves, C over Q, with a certain type of marked point, namely a hyperflex. So a non-hyperelliptic genus tree curves is embedded canonically inside P2 as a plane quartic. And hyperflex means that if you take the tangent line at the point P, then it's a contact of order 4. So it only hits the curve in that point. All right, and whatever this abstract description is, you can also see it as just those curves defined by the following plane equation involving 6 coefficients, and where 2 are the same if you can scale by some factor, depending on the coefficients. And again, there is a suitable height you can define. And so 2 consequences of the main theorem, plus some extra work on relating that to rational points, lead to those concrete consequences. So majority of curves in this family have at most 26 rational points. In fact, if you're willing to restrict to a small proportion, then you can prove that a positive proportion in F have only 1 rational point, namely the marked point to begin with. And so the first one is proved using a Chabot method at 7. And the second one is proved using techniques a la Poonen and Stoll. All right, so this is a maybe very concrete consequence. So if there are no questions about this, then let me move on to saying a few words about the proofs. All right, so let me say a few words about the proof. So I'm going to focus on the proof of theorem 1. And so that's the proof of the construction of orbits. And so let me explain this. So first, what we're going to do is we're going to construct an identity element corresponding to the identity element of the Selmer group. So because this should always have an orbit. And in fact, this is very easy. Turns out that you can construct this in a very nice way. This is akin to the companion matrix of a polynomial, and the general construction is called the constant section. And the second step is to sort of twist this orbit and prove a relation with Galois cohomology. So this bijection below here typically falls under the rubric of arithmetic invariant theory. And what it says is that if you consider all orbits of VQ such that over Q bar they become conjugate to this kappa C, then those are in canonical bijection with this kernel of pointed Galois cohomology sets. So these are Galois cohomology, but G is highly non-abelian, so this is going to be just a pointed set. And so this kernel where this is a stabilizer of the action, and the map is induced by the inclusion. And in fact, this bijection is very explicit. If you have a orbit here that's GQ bar conjugate, you can just construct a co-cycle very easily. And the sort of real first theorem in this setup is due to Thorne and his thesis, and it's one of his main results. And it says that the stabilizer here can be canonically identified with the two torsion in the Jacobian as Galois modules. So maybe you can start to see the connection with the two-Selmer group, or how one could possibly embed the two-Selmer group inside the orbits. Because phrased in this way, and using these step 2, we now just need to show that the two-Selmer group of the Jacobian gives rise to orbits. So if you consider the following composition, where the first map embeds the two-Selmer group inside J2 by definition, then we transport along the isomorphism of Thorne, and then we map it into G. Then we need to show that this composition is trivial. Because if we know that, then we know that every element gives rise to an orbit. Okay, and in fact, using some weak form of the local global principle for H1 of G. So G is going to be a split semi-simple group, and it turns out that the kernel of the map, which is again just merely a map of pointed sets, is trivial. We need to show, or we're reduced to showing, using definition of the two-Selmer group, that if you consider instead the following composite for any field extension over Q, in fact, only looking at completions of Q suffices, but we can prove it for any field extension. We need to prove that for any field extension, the following composition is trivial. Or again, you map it into H1 of G. All right, and that will be exactly what we'll show. And I'll explain this in the next slides. And I should say that sort of this general strategy was well known. And so in his thesis, the triviality of this composition, it's stated as a conjecture in the end. And here is sort of where my contribution comes in. So let me explain how to do this. So the idea will be to consider these things universally. So for a given family of curves, we can just bundle them all together and build a geometric object that fibers over some base space where the fibers are all the smooth curves we want to consider. And similarly, we can take the relative Picard functor and or the relative Jacobian, and we get a relative Jacobian. So let me just be very concrete. So if you look at the A2 case, then C in this case is going to be equal to the relative Jacobian because it will be elliptic curves. This will be the closed subscheme of P2 times the parameter space A2 minus the discriminant locus defined by the universal Weierstrass equation. So it's a universal elliptic curve with a short Weierstrass equation. Y squared equals x cubed plus ax plus b. So here a and b are the coordinates on A2, and y and x you should interpret as homogeneous coordinates on P2, or like dehomogenized coordinates. And in fact, we're describing a closed subscheme of here. So, all right, so we're bundling all these elliptic curves together. And so recall here this map, whose composite we want to show is trivial. So every point on the Jacobian gives rise to a cohomology class. Let's call it alpha p in here. And the next observation is that we don't only bundle together the curves and the Jacobians, but also all these cohomology classes. And the reason we can do this is that this H1 is the classifying set of G torsors on spec K. So using this interpretation and using some formal nonsense, you can write down a G torsor over this curly J, call it curly T, that interpolates all these classes. So interpolates it in the sense that, so what do I mean by interpolate here? It means that if I take an element of this curly J, a K point, this will give rise to a K point on some Jacobian. Then this, the fiber of this torsor along P, its class will be equal to alpha P in H1 kg. Okay, so now we need to prove that this torsor is trivial above every K point of curly J. And what we're actually going to prove is something slightly stronger, namely that this torsor here over curly J is Zariski locally trivial. So in particular, this implies that alpha P is trivial for all P, because if you take a K point, then you can, so Zariski locally trivial, maybe I should first say that, means that there exists a Zariski neighborhood or Zariski cover of curly J, such that above that cover, the torsor becomes trivial. And if you take a K point and you just take an open neighborhood around it, then this shows the triviality of every class alpha P. And I should say that this is not formal, because like for a group like GLN, every torsor is Zariski locally trivial, because that just corresponds to vector bundles. But for most reductive groups, this wouldn't be the case. So, well, if you take PGLN or PGL2 from our example, turns out that G will often be an orthogonal group, and then that will certainly not be the case. That it will only be a tau locally trivial a priori. Okay, so that's sort of the main theorem I want to explain to you how to prove. And I guess the main observation in the way that I've set it up here is that even though the fibers of this morphism, they're curves and they're abelian varieties, so they're not necessarily simple spaces, the crucial fact is that these spaces themselves, they are relatively simple as a total space. So let me show you how that works. So there are two essential ingredients to prove this theorem. The first one, as I said, is the geometry of this curly J. And so one way of expressing that the space is simple is that the total space is rational. So it's a rational variety. And how do you prove this? So I'll give an example after I say how to prove this in general. So the way to prove this is to actually extend the definition of curly J to the whole affine space of coefficients, including the curves that are singular. Excuse me. So if you have a singular curve, you can still associate a Jacobian to it. This will be a smooth group scheme, but it won't necessarily be proper. It will actually never be proper. And the theory of compactified Jacobians adds to line bundles other types of sheaves, namely certain types of rank 1 torsion-free sheaves, such that the corresponding scheme you get will be something singular, but it will be proper. So this morphism here, so this extend the morphism from curly J to the affine space deprived of the discriminant locus, And this morphism will be a proper morphism. And it won't be smooth. But sort of the crucial fact is that, again, this total space is smooth. And in fact, the BB decomposition, the Bialnicki-Birula decomposition, which is a tool often applied in, for example, geometric representation theory, for a certain GM action, torus action on G, implies that this decomposes into affine spaces. Like this. So, it's a fact that curly J is dense in this complexified Jacobian. So this implies the result. So let me give you an example. So in the A2 case, it turns out that the complexified Jacobian of a singular genus 1 curve, that's just the curve itself. So for example, if you take a nodal cubic, then the Jacobian will be GM. And the way that you compactify GM is by adding, by putting it in a nodal curve. So this curly J here, it will simply be the universal Weierstrass equation, but just over all cubic curves. So closed subscheme of P2 times A2. So here I really want to consider the whole of A2, not deprived of its discriminant locus. Again, defined by the Weierstrass equation. And here we can see very easily that this has simple geometry, because this space, you can look at its affine patch, the standard affine patch of X and Y, and the patch at infinity, so the, let's say, line at infinity. And if you intersect this with the defining equation, or if you consider the points in this defining equation, then the first one is given by quadruples x, y, a, b that satisfies the Weierstrass equation. But now a and b are variables, so we can just say b equals all the others, and that will just be an A3. And the line at infinity, there will be 1 for every point above A2. So we get an A2 here. So that's sort of a very concrete thing. And if you want to prove this for other curves, then you need more machinery. But yeah, it's very simple in this case. Okay. So let's see what the second ingredient is. So now that we know that the geometry of the space is easy, we can just try to look for general results on torsors on spaces with simple geometry. And here's one that we will use. So what's the setup? So I have an open subset of affine space, and it's large in the sense that the codimension of the complement is at least 2. Okay, and we're going to take a G torsor over U. And here we have our G, but this can be any reductive group. And suppose that for one point of U, one rational point of U, this torsor is trivial. Good, then the conclusion is that this torsor is trivial for every point of U. And in fact, even more is true, it's Zariski locally trivial. All right, so this ingredient here follows from, so I should say, follows from results of Coyotelin. But hasn't been written down before, but I could imagine that it was well known to some people, or it is well known. And let me just write this down pictorially. So suppose this is U, we have our X here. Then this theorem sort of says that the triviality of the torsors sort of propagates or in U. So if you take any other point, then the torsor will also be trivial over that point. And here we really make use of the simple geometry of this U. This will definitely not be true in general. Yes, so, all right, and then combining those two ingredients, we need one other sort of finishing touch that binds everything together. And that's a application of something called the Grothendieck-Serre conjecture, which is a general conjecture on torsors under reductive group schemes over integral regular schemes. And the sort of consequence that we'll need is the following, namely, if we can prove that this torsor is generically trivial, so it's trivial over the generic point of curly J, then it's actually Zariski locally trivial. Okay, and so this follows from the Grothendieck-Serre conjecture for regular schemes over an infinite field. And this was established by Fedorov and Panin 10 years ago or so. And all right, so let me briefly combine all the ingredients and summarize the arguments. So we want to prove that this curly T is Zariski locally trivial. So by the first ingredient, we know that there exists some open subset V in curly G, which is also an open subset in some affine space, right? Because it's rational. And here, this step 2, I didn't explain very properly, but it turns out that the restriction of this torsor to V, you can actually extend to a torsor over a larger subset of AN that satisfies this hypothesis of the second ingredient. So you extend it to a larger subset U with this property. And I didn't explain this, but it basically follows from studying nodal curves in great detail, because codimension 1 points of the complements will precisely correspond to nodal generations. And we understand those so well that we can extend the torsor over those as well. All right. And so we're in the setting of the second ingredient. So we only need to prove that above 1 point, the torsor is trivial. And here you can apply a very funny trick. So it's true that there exists a point in V above which this torsor is trivial, because, well, this curly J is a rational variety. So its rational points are dense, for example. And it's an abelian scheme over some base. So there's a multiplication by 2 map. This map is dominant. So that means that the image of the rational points under this map are dense in here, which is strange because the fibers of this map are abelian varieties and we don't really understand their rational points, but somehow the total space is rational points. It's very easy. And well, the third part that I need to say is that alpha P equals 1 if P is in 2 times JQ. Basically, because the definition of alpha of P started with applying the 2 descent map. But if you lie in 2 times JK, then you're already trivial in the first step. So since V is an open and 2JQ is dense, they will intersect. So there will be a point where it's trivial. So by our second ingredient, this implies that this torsor is Zariski trivial. So by this generalities on torsors on affine spaces. And by the Grothendieck-Serre conjecture, we know that the torsor is trivial over the whole of curly J. Basically, because we only needed to know that it was generically trivial. But if once we know it over an open subset, then we definitely know it over the generic points. So yeah, so that's sort of the summary of the argument. Okay, so that was sort of the explanation in broad terms of the proof of theorem 1. I should say, so here we've used properties of the compactified Jacobian very heavily. And it turns out that if you want to prove the existence of integral representatives, then in a very similar fashion, you can use again or exploit again the properties of compactified Jacobians. So you'll use some other type of results, namely Bertini theorems and purity results. But I just wanted to end with mentioning that compactified Jacobian is not only useful for proving this theorem, but also for constructing integral representatives. So that's sort of the main player. Okay, so that was the end of my talk, and thank you for your attention, and happy to answer any questions.
Great. Well, let's thank Jef for a wonderful talk.
Yeah.
Are there any questions for Jef? I kind of have a question if nobody else does. Is there any hope of getting anything geometric to happen on the, you have other kinds of Dickon diagrams like BC and F4 and G2. Is there anything on the geometric side that might correspond to this that you could do something similar, or is there just nothing there?
So yeah, that's a good question. There is, so on the representation theory side, there's again distinguished grading, and you again have this Finrod representation. And on the geometric side, you will have a family of curves, but it will be a family of curves together with some extra symmetry. So the generic member of the family will have a non-trivial automorphism group, and it's hard to say something in a uniform way, but specific cases have been analyzed, and it turns out that the symmetry gives rise to either abelian subvarieties or isogenies on the Jacobian, and you'll be able to say something about the isogeny Selmer group. And this is actually like very similar to, well, I guess a general paradigm maybe in Lie theory, where you can study non-simply laced Dickon diagrams using a simply laced one and an involution, or an automorphism using some sort of folding procedure. So G2 would be like D4, where you identify the nodes, and and so I have a paper where I look at F4, and then it turns out that you get a family of prim varieties, and you can say something about the statistics of those prim varieties. So the picture is a little bit less uniform, but there's still a lot of interesting things to say. Yeah.
Did somebody ever say anything in the G2 case?
Yeah, so the G2 case was handled in a classical way, not necessarily using this language. So yeah, you can also consider like 3 or 4 gradings. And it turns out that what is quite interesting is a certain 3 grading on G2.
Yeah, G2 has a 3 grading.
Yeah, and that corresponds to studying the isogeny Selmer group of a J-invariant 0 elliptic curve. So if you consider like y² equals x cubed plus k, then the tree torsion has a Galois invariant subgroup, and the isogeny corresponding to that you can study this using this representation, but it's very small. I think it's just binary cubic forms, GL2 acting on binary cubic forms or something. So
yeah. I see. Cool. There was also a question in the chat. Jinbo asks if your work can establish any special cases of BSD.
Yeah, I have no idea. Like, I guess what this is alluding to, the fact that like others in the past have established, well, the BSD conjecture for the majority of elliptic curves in some sense. Well, for that, you would need to know something about, say, the analytic rank and so on. And you would also need to know, I think, very precise things of weak forms of BSD and analytic rank 0 or 1 for higher dimensional abelian varieties. And it's an interesting question, but I wouldn't expect that the current technology would allow that. Yeah.
All right, I have a question. An analytic one about you have the upper bound, but you didn't have the asymptotics, presumably because you can't do a square-free sieve. Could you maybe clarify what that analytic difficulty is, or is it just that the degrees of the polynomial are too large so you just do sieve up to some q and then you just get a bound? Is that the point?
Yeah, so trying to see what the easiest way to say it. So
I mean, I've seen it in other problems, but I'm just curious in your situation.
so the upper bound is relatively formal because yeah, you're just exactly, you're sieving up to a certain bound and take the limit, and then but to get the lower bound, I think, yeah, you need to know something about yeah, the proportion of square free values of the discriminant polynomial, or it's the orbits, and yeah.
Have you tried to sieve? Is what I guess, you know, there's sieve methods, but I'm sure that you've or somebody's tried.
Yeah, so well, so in the higher grading case, there's some general method that I think usually in the papers of Bhargava and others, they write it down for each representation, but you can write it down in a very general way. But for like 2 gradings, the elliptic curve case, I think you can reinterpret it as using some exceptional isomorphism. For example, you can embed A2 in G2, and I think studying this embedding, well, you have this problem with like that you have points. What is it again? Like you have divisible by a prime for mod p reasons and mod p squared reasons, and one is easy and one is hard, and you want to convert one and the other. And the reason that you do that is you do some clever representation theory to, and maybe embed it inside something or so. And well, so it always seems to be a very clever trick to do. But I'm not aware of in the cases that I was considering that of any other solution for this problem except for the A2 case. So yeah, so but, I mean, that would be very interesting to know. Yeah, I think that's a big open problem in the.
Thanks.
Cool. Any other questions from anybody? Even in chat? I don't think there's anything in chat. Well, if not, let's thank Jef one more time.